Quantum Weirdness, Part 3, Bohr Plays Poker. The great extension of our experience in recent years has brought light to the insufficiency of our simple mechanical conceptions and, as a consequence, has shaken the foundation on which the customary interpretation of observation was based. Physics is to be regarded not so much as the study of something a priori given, but rather as the development of methods of ordering and surveying human experience. Niels Bohr received his Nobel Prize in Physics in 1922, a year after Albert Einstein's award in 1921, though both were given their awards at the same ceremony in 1922 in Stockholm. Einstein and Bohr had a deep fondness and respect for each other, and while they certainly had their philosophic disagreements over the years, particularly over how to interpret the new physics, their admiration for each other lasted till the end of their lives. It has been mentioned in several books dealing with the Einstein-Bohr debate that Einstein was more of a realist when it came to science, and Bohr was more of an idealist. This description of their differences is too simplistic to be accurate. Niels Bohr was deeply involved from the very beginning with the revolution that took place in physics during the first quarter or so of the 20th century. Indeed, his early model of the atom, based in part upon Ernest Rutherford's investigations, was an elemental bridge to later quantum theories that eventually made it obsolete. It was because of Bohr's simple but predictive explanation of the spectral lines of the hydrogen atom that significant progress was made in unearthing the inner workings of physical constants at the subatomic realm. Bohr, unlike Einstein, enjoyed working with a series of devoted students and loved the to and fro of debating the implications of the latest findings in atomic theory. It has been convincingly argued by Donald Murdoch in his groundbreaking study, Niels Bohr's Philosophy of Physics, that Bohr was less an idealist and more a pragmatist when it came to interpreting the implications of quantum mechanics. What this means is that Bohr tried to let the physics itself lead to its own interpretation and not try to impose upon it his own already made philosophy. This is best captured in one of his most famous quotes, where Bohr ruminates, "When it comes to atoms, language can be used only as in poetry. The poet, too, is not nearly so concerned with describing facts as with creating images. It is wrong to think that the task of physics is to find out how nature is. Physics concerns what we say about nature." What Bohr reveals here is a deep understanding of the very limits of the scientific enterprise and how human investigations of objective phenomena are intimately limited by its own apparatus. This raises a philosophic conundrum which is age-old and is perhaps best articulated by Immanuel Kant. As the website Philosophy Pages illuminates, according to Kant, it is vital always to distinguish between the distinct realms of phenomena and noumena. Phenomena are the appearances, which constitute the our experience. Noumena are the presumed things themselves, which constitute reality. All of our synthetic a priori judgments apply only to the phenomenal realm, not the noumenal. It is only at this level, with respect to what we can experience, that we are justified in imposing the structure of our concepts onto the objects of our knowledge. Since the thing in itself, Ding an sich, would by definition be entirely independent of our experience of it, we are utterly ignorant of the noumenal realm. Thus, on Kant's view, the most fundamental laws of nature, like the truths of mathematics, are knowable precisely because they make no effort to describe the world as it really is, but rather prescribe the structure of the world as we experience it. By applying the pure forms of sensible intuition and the pure concepts of the understanding, we achieve a systematic view of the phenomenal realm, but learn nothing of the noumenal realm. Math and science are certainly true of the phenomena. Only metaphysics claims to instruct us about the noumena. To grapple with quantum indeterminacy, Bohr developed his idea of complementarity to help explain one of the chief aspects of how nature reveals itself. And because nature is embedded with complementarity, it is nay impossible to exorcise it away from scientific investigations. In fact, Heisenberg's principle of uncertainty is a defining example of how nature is paired and manifests in ways similar to the Taoist notion of yin and yang, or in this case, wave and particle. As the Wikipedia entry on complementarity elaborates, a profound aspect of complementarity is that it not only applies to measurability or knowability of some property of a physical entity, but more importantly, it applies to the limitations of that physical entity's very manifestation of the property in the physical world. All properties of physical entities exist only in pairs, which Bohr described as complementary or conjugate pairs, which are also Fourier transform pairs. Physical reality is determined and defined by manifestations of properties which are limited by trade-offs between these complementary pairs. For example, an electron can manifest a greater and greater accuracy of its position only in even trade for a complementary loss in accuracy of manifesting its momentum. This means that there is a limitation on the precision with which an electron can possess, that is, manifest, position, since an infinitely precise position would dictate that its manifested momentum would be infinitely imprecise, or undefined, that is, non-manifest or not possessed, which is not possible. The ultimate limitations in precision of property manifestations are quantified by the Heisenberg uncertainty principle and Planck units. Complementarity and uncertainty dictate that all properties and actions in the physical world are therefore non-deterministic to some degree. Bohr's overall view dovetails with Ernest Mach's and represents a form of logical positivism. As Jan Fay states, Bohr's idea of complementarity thus understood was not so different from Neurath's and Carnap's view of relating all statements about theoretical entities to statements about observable things expressed in terms of protocol sentences. Against Einstein's metaphysical attitude towards a physical reality consisting of things in themselves, Bohr could just reply that it does not make sense to operate with a conception of reality other than one which can be described in sentences concerning our empirical knowledge. If experimental knowledge does prohibit an ascription of a precise position and a precise momentum at the same time, it does not make sense to talk about a free, undisturbed electron to have such values anyhow. It in this sense that Dugald Murdoch sees Bohr's philosophy as pragmatic and not preset. Whereas Einstein would follow his intuition about how nature must or should work, Bohr argued for following the data and letting it determine whatever philosophical course would follow. This is wittingly captured with Bohr's reaction to Einstein's famous dictum that God doesn't play dice when he quipped, "Einstein, don't tell God what to do." It can also be that because Bohr worked so closely with those who developed quantum mechanics, specifically his star pupil Heisenberg, that he was more acquainted in a practical way with what worked and what didn't. Bohr got his hands dirty with quantum theory perhaps in a way that Einstein didn't, and due to that was more willing to allow for its radical implications. As Bohr warned, those who are not shocked when they first come across quantum mechanics cannot possibly have understood it. Bohr became the champion of the single most popular philosophic interpretation of the new physics, which would later be known as the Copenhagen interpretation because of the location of his institute. In many ways, Bohr's reasoning is akin to what we find in Plato's allegory of the cave, as found in his Republic, but with one very telling caveat. In Plato's story, we learn that prisoners shackled in the cave cannot actually see the light itself, which is casting the varying shadows on the wall. And only later, when unhinged, can they progress from the rudimentary impressions to clearer shapes and outlines, until the full luminosity of the light explains more fully how all these images were generated. In the quantum mechanical world, we are in a similar position, since we cannot actually know both the position and the momentum of any single electron, but only its probabilities, and even then how we measure such an outcome predetermines its wave or particle manifestation. What the electron is really doing, nobody knows. Apparently, nobody can know what a single bit of matter is ultimately doing, since even that definition of bit of matter is itself a construct, a theoretical map in order to make sense out of one aspect of what appears at such minute levels of matter. What we get when we penetrate the subatomic realm isn't, to quote Kant, the thing in itself, but only what appears visible to our intervening devices, and since we cannot intrude into that realm without some type of instrument, even a single photon cascading off an electron causes a disruption of the assumed virgin state. We don't unlock nature pure and pristine, but as nature reacts to our measuring devices. In other words, we cannot unlock nature as nature, or electron as electron, or matter as matter, since we are invariably altering what we are examining. We might occasionally acknowledge this interference even at the macroscopic level. Sociologists and psychologists are well versed in interpreters' biases in grappling with raw data. But at the quantum level, it looms so large and is so evidential that its impact cannot at any instance be ignored. Heisenberg's principle of uncertainty isn't merely a temporary limit to man's knowledge, according to Bohr, but a fundamental statement about what that knowledge is. It is for this reason that Plato's allegory is instructive, since we are not in the position of the narrator to look objectively upon the cave, from the outside and the inside simultaneously. Rather, we are the prisoners in the cave, and only from that position can we both induce and deduce what may or may not be ultimately real, but in so doing we are still at the Kantian level of phenomena. What quantum mechanics revealed was precisely this epistemological impasse, and how it plays out in trying to form a picture about reality. Reality we can never know, since that very concept is itself a fiction which implies that we can somehow act as an objective narrator to the entire cosmos, with a 360-degree purview and a level of certainty, which implies that we are impartial witnesses to a play with a beginning, middle, and an end. No, we are literally like the prisoners in Plato's allegory of the cave, limited by our very existence in what can and cannot know. For Bohr, this wasn't merely a philosophical extension of his Kierkegaardian leanings, but the very result of what quantum mechanics revealed about our ability to come to grips with nature and how it responds to our introspections. As Bohr put it is wrong to think that the task of physics is to find out how nature is. Physics concerns what we say about nature. Or, as Bohr himself discovered, for a parallel to the lesson of atomic theory regarding the limited applicability of such customary idealizations, we must in fact turn to quite other branches of science, such as psychology, or even to that kind of epistemological problems with which already thinkers like Buddha and Lao Tzu have been confronted, when trying to harmonize our position as spectators and actors in the great drama of existence. Everything we call real is made of things that cannot be regarded as real. It is little wonder, therefore, that so many eminent scientists have had such ambivalent reactions and feelings to the implications of quantum mechanics. This is epitomized by a close reading of the following quotes garnered from the Quantum World website. Quantum mechanics is magic. Daniel Greenberger.
I did that.
Those who are not shocked when they first come across quantum theory cannot possibly have understood it. Niels Bohr. If you are not completely confused by quantum mechanics, you do not understand it. John Wheeler. It is safe to say that nobody understands quantum mechanics. Richard Feynman. If quantum theory is correct, it signifies the end of physics as a science. Albert Einstein. I do not like quantum mechanics, and I am sorry I ever had anything to do with it. Erwin Schrödinger. Quantum mechanics makes absolutely no sense. Roger Penrose.